My name is Neil. I'm a postdoctoral researcher in Weizmann Institute. I want to thank you for attending my talk entitled Learning Task-Based Analog to Digital Conversion for MIMO Receivers. It's a joint work with Ruud van Sloan and his student Iris from TU Eindhoven, and with Gosha Tsintzadze and my superb mentor Yonina Eldar from Weizmann Institute. The talk is about signal acquisition. Signal acquisition lies in the analog to digital frontier, where physical signals are converted into sequences of bits. This operation consists of three stages. First, we have our waveform, which lies in continuous space, but it is only measured in discrete locations dictated by our antennas or our sensors. The signals observed at each one of those sensors is converted from continuous time to discrete time via sampling, yielding a set of continuous amplitude samples. The set of samples are converted into a digital representation, a set of zeros and ones, via quantization. And this set of zeros and ones can now be fed to processing in the digital domain. This digital representation has to maintain several properties. First, it has to be accurate in the sense that it contains the semantic information with respect to the analog waveform. Second, it has to be compact, namely we do not want to use an infinite number of bits to represent waveforms. Third, it has to be hardware limited, namely it has to be something we can actually build. It has to represent something we can actually build in hardware. Now, the conventional approach to study signal acquisition is to exploit structure. Namely, if, for example, our signal is band limited, we know how we can acquire it such that it can be perfectly recovered or recovered with some error. If the signal exhibits sparsity in some domain, we also have approaches to tackle this. The thing is that analog to digital converters, when it operates with wideband signals and at high bit rates, it tends to be very costly and power consuming. This led us over the last 2 years to look into what's called task-based acquisition. And the rationale of task-based acquisition is to account for the fact that in practice, usually analog signals are not acquired in order to be reconstructed, but acquired in order to extract some underlying information. There is some task. For example, in communication, we do not care about the electromagnetic waveform propagating through the channel. What we're actually interested in is recovering the constellation symbols embedded into this waveform. And this led us to the question whether we can operate reliably or at least mitigate the distortion induced by low rate acquisition by accounting for the fact that the signal is acquired for a specific task. Now, to do that, we considered this system in which the analog to digital converters are modeled as uniform quantizers with some dynamic range and some partition of the decision regions. And then the overall system also included some pre-acquisition mapping, some analog combining, whose output are fed to those identical ADCs, and then goes into digital processing. And we optimize the overall system, namely both the analog combining, the quantization mapping, and the digital processing in light of the task, not in order to recover the observed signal. Now, we did this for several specific tasks. We consider a linear task in which the information we're trying to recover can be modeled as a linear function of the observations. We also considered quadratic tasks. And now, the thing is that this analog combining, which is required in order to exploit the presence of the task here, is not such a far-fetched model. It's actually exactly what is done in hybrid MIMO receivers, in which are commonly studied in millimeter wave communication, in massive MIMO communications. And there, the motivation for using this pre-acquisition analog hardware is to reduce the number of costly RF chains. However, note that here the ADCs are only modeled as quantizers. We're actually neglecting the part of sampling. Still, the analytically designing analog to digital quantizers is a challenging task. First, it requires full knowledge of the underlying model relating the observation and the task. We had a different result for linear model, different result for quadratic model. And this may be complex in some cases. The statistical relationship may not yield such a nice analytically tractable form. And if we do not know it, or we have some estimation errors of the underlying model, then it will inevitably introduce errors. This motivates us to consider a data-driven approach, which does not require to explicitly knowing the underlying statistic. It is capable of learning them from data. Furthermore, our previous approaches modeled ADCs only as quantizers, but in practice, ADCs consist of both sampling and quantization. So in this current work, we will look at a data-driven, machine learning-based implementation of task-based acquisition systems accounting for both sampling and quantization. We'll do so by first introducing this model for the system and the signal, and then we will show how its parameters can be learned and present a numerical application of it to MIMO symbol detection. Now, this complex figure down below here is the model, is the system we are considering. It first consists of a task, which is a vector, which we are interested in, which we want to recover. For example, in communication, it can be the symbols which were transmitted. What we are observing are a set of analog signals, x1 to xn of t, observed over this finite time 0 to t, and they are statistically related to the task via some conditional distribution measure f of x given s. Now to our acquisition system. Our acquisition system first consists of this analog filter with impulse response h. The outputs of the analog filter are fed into identical scalar ADCs, consist of sampling. The sampling is modeled via convolution with delta functions at the sampling time instances tj, and quantization, which is modeled via a sum of step functions where the parameters bi dictate the decision regions and the parameters ai dictate the values assigned to the decision regions. Note that this model accurately represents the operation of sampling and quantization, but it is not restricted to uniform sampling and it is not restricted to uniform quantization. We do not assume that the time instances tj are uniformly spaced over 0 to t, and we do not assume that the quantization decision regions are equally spaced. Now, the output of these digital quantizers of the ADCs is fed to digital processing, whose target is to recover the task of interest. Now, in order to optimize it, we need to make some model assumption, and our assumption is that the measurement and the analog filter are spanned by dense sampling, namely that the analog signal and the impulse response of the filter can be faithfully represented by their samples over some dense grid of L samples. Now, once we do this, we can also represent the samples of the input to the ADCs using only the corresponding samples of the observed signal and the filter. And then we obtain this discrete model, and this discrete model does not lose any information, so we can only optimize with respect to that discrete model. So obviously, if this is only an approximation, then there will be an additional error term which we are not optimizing with respect to, which stems from the fact that we have considered a discrete grid. Obviously, if this grid is dense enough, then the additional error will be negligible. Having done that, having obtained a discrete model, we can now consider the whole system and model it as a neural network, which we are trying to optimize. It will consist of an analog filter, which is the matrix H, which can be treated as this analog pre-network. Then there's the sampling time dictated by the sampling time instances, the quantization, which is dictated by the decision regions and their associated values, and the digital processing, which can be modeled as a linear network. And having done that, we can now essentially optimize the whole thing using stochastic gradient descent with backpropagation. Yet, there is a problem here, and this problem stems from the fact that, well, quantization is a non-differentiable mapping, namely it is differentiable, but it nullifies the gradient almost everywhere. Furthermore, sampling is also a non-differentiable operation, which means that we cannot propagate through this, and we cannot train the whole thing in an end-to-end manner. So in order to tackle that, we will adopt what's called a soft-to-hard approach, in which we approximate non-differentiable mappings, hard ones, using differentiable ones during training, and then during inference, we only fix the hard mappings. For example, sampling, we know that you can model it using convolution with delta functions, and we know that delta functions are the limit case of Gaussians, so we can replace those delta functions with Gaussians and obtain something that we can backpropagate through. Similarly, quantization is modeled as a sum of step functions. Now, step functions can be modeled, approached using a sequence of hyperbolic tangents. So if we replace the sine functions with hyperbolic tangents, we get a differentiable approximation, and this is exactly what it looks like. This is the orange plots are the hard functions, while the blue plots are the soft functions. And then we can see that the blue functions are how we model the operations during training, while the orange curves are the hard mappings, which are learned during training and fixed during inference. And this also allows us to learn non-uniform mapping, because we can actually learn now the time instances, the decision regions, and their associated values as parameters of the network. Now, by doing that, we actually are able to learn the overall task-based acquisition system. We can test this for a specific numerical setup in which we consider a MIMO symbol detection. We have a set of K users, and the signal is observed using 6 antennas over some time-varying channel. And we consider a task-based acquisition system in which we have 4 analog to digital converters. Each one acquires 8 samples, 4 samples with 8 bits, overall number of 8 bits. And for the digital filter, we assume some fully connected classification network with a single hidden. So let's see how well does this system performs. Now, the blue curve here is the performance achievable by our proposed system. This is the bit error rate versus the SNR. Now, for comparison, the black curve here is the performance achieved using the MAPS rule applied only to a uniform sampling of the observed channel output without any analog combining. And as we can see, the performance is quite close. We're actually able to approach unquantized performance. For comparison, the purple curve here is the performance achievable had we applied uniform sampling and uniform quantization without analog combining to the output of the channel, and then apply the map rule to those quantized representations. And as we can see, it performs much, much more poorly because it does not account for the task in acquisition, so it loses its ability to accurately recover the signals. Now, the gains are not only in our ability to approach unquantized performance. We can also consider the case in which there is some uncertainty in the underlying model. Now, we know that model-based approaches, they perform quite poorly when there's inaccurate knowledge of the underlying channel. For example, the black curve, the dashed black curve here is the performance achievable by the unquantized uniformly sampled map applied with some uncertainty. Furthermore, the red curve here is the performance of the map applied directly to the continuous time signals without any sampling constraint or any quantization constraints, but with inaccurate knowledge of the channel. As we can see, it hits some error flow, which it does not go below regardless of the SNR. Now, for comparison, the dashed blue curve here is the performance of our proposed system had it trained with the same uncertainty over a variety of channels without knowing in advance to exactly which channel it is going to be applied. So these results actually demonstrate the ability of this deep task-based acquisition system to approach unquantized performance by learning to reduce the dimensionality, to combine the analog signals prior to their acquisition. Furthermore, we are also demonstrating improved robustness, uncertainty compared to model-based approaches, which stands for our data-driven strategy. So in this talk, I've showed how one can learn analog to digital conversion acquisition systems in light of a task by combining deep learning with hybrid acquisition system models. We optimize nonlinear ADCs using a soft-to-hard approach, and we show that it is allowed to approach unquantized performance, demonstrate improved robustness to uncertainty. It also gives rise to many other interesting questions. For example, can we optimize the trade-off between sampling rate, bits, number of ADCs in light of an overall bit budget we are subject to? This is not something we did here. We considered fixed number of ADCs, fixed number of quantization decision regions, and so on. And this actually motivates us to look into meta learning as a future approach to extend this current work. But with this, I will wrap up. And I want to thank you very much for attending my talk. And if you have any questions, please feel free to contact me. Thank you very much.